Yeah. Hello everyone. This is continuation video on solid state part 2. In the part 1, we talked about types of solids like amorphous solids and crystalline solids. But for GE, we have totally crystalline solids. But all differences between crystalline solids and amorphous solids in the first video we discussed. Now, in this video, let us discuss classification of crystalline solids. Already in the first video also I told you the first part of the solid state and the last part of the solid state, they are somewhat memory based. And now let us take what are the different types of crystalline solids. Crystalline solids. So crystalline solids based on the nature of attractive forces between the constant particles. Constant particles means the particles which are forming the solid. Sometimes ions will form solids, sometimes atoms will form solids, in some cases molecules will form solids. So here constant particles, between the constant particles, what are the attractive forces present? So based on intermolecular forces, operating in them, based on interparticle forces or intermolecular forces, all crystalline solids are classified. They are classified into four types. What are the four types of crystalline solids? The first category, molecular solids. Second category, ionic solids. Third category, metallic solids. And the fourth category, covalent or network solids. So solids are classified into two types, crystalline and amorphous. Crystalline solids are further classified into four types. This classification is done based on nature of interparticle forces. And in this, the first category, molecular solids, it's very clear, right? Molecular solids means they are made up of molecules. Ionic solids are made up of ions. Metallic solids are made up of metal kernels. Covalent solids or network solids are made up of atoms of same or different elements. So always the students confuse between molecular solids and network covalent solids. Here you will understand the difference. So these molecular solids are further classified into three types. These molecular solids are further classified into three types because that molecule may be non-polar or polar. If the molecule is non-polar, that is non-polar molecular solid. Dipole moment, of course you know polarity, how to check. So here, if dipole moment is 0, then we can say that is non-polar molecule. If molecule is polar molecular solid. And we can say in case of polar molecular solids, there are dipole-dipole interactions, but the extreme form of dipole-dipole interactions are called hydrogen bonds. This is also polar, but when we compare with the dipole-dipole interactions, the strength of hydrogen bond is little more. Hence, the molecules may be non-polar molecules, molecules may be polar molecules, molecules may be hydrogen bonded molecules. So in this video, we have to talk about the different types of crystalline solids. Crystalline solids based on the nature of constant particles also we can say. If the particles are molecules, molecular solids. If the particles are ions, ionic solids. If the particles are metal kernels, metallic solids. If the solid is made up of large number of atoms of same or different elements which are held by network of covalent bonds, then it is called covalent solid or network solid. And these molecular solids are further classified non-polar, polar and hydrogen bonded. So we have to talk about all different categories, but I told you also yesterday with the help of diagrams. First, let us take molecular solids. Very clear, right? Molecular solids are made up of molecules only. Molecular solids are made up of molecules. What kind of molecules? Non-polar, polar, hydrogen bonded. Based on that, these are further classified into non-polar molecular solids. But let us understand these non-polar molecular solids. For example, let us take this is a molecule, or if you are not comfortable, you can assume atom. This is another atom. This is one molecule, this is another molecule, or this is one atom, this is another atom. Whatever it may be, no issue. But actually, at center, can you see there is nucleus, nucleons, and distribution of electrons around the nucleus is symmetrical. There is a symmetrical distribution of electrons around the nucleus. But at a particular instant, so what happened is, you can see here the distribution of electrons in the first case and second case if you observe, and here in the first case the symmetrical distribution of electrons it has. But at a particular instant, you can see electron cloud is concentrated at one end. As a result, symmetrical distribution becomes unsymmetrical. Whenever symmetrical distribution is whenever electron distribution is unsymmetrical, what do we call? Instantaneous dipole is produced. Instantaneous dipole, charge separation. Here electron cloud distribution is symmetrical, but here it is unsymmetrical. And because of this unsymmetrical distribution, instantaneously at a particular instant, what happened? Some, what do we call, dipole, but that is not a permanent dipole. That is a temporary dipole. And whatever the temporary dipole produced, it causes distortion of electron cloud in the second molecule. This molecule is inducing dipole moment in the second molecule. Because of this molecule, distortion of electron cloud will take place. As a result, you can see earlier the molecules are symmetrical, but here at a particular instant they are unsymmetrical, and here there is negative charge, and here there is negative charge electron cloud, and this is a positive charge, and what do we call, these are dipole interactions, but very clear they are not permanent dipoles, temporary, and these are called London dispersion forces. So ultimately, if you ask non-polar molecular solids, what are the intermolecular forces? Intermolecular forces are London forces. How London forces are developed? Like this, London forces are developed. London forces are weak forces. When compared to dipole-dipole interactions, these are weak. When compared to hydrogen bond, dipole-dipole interactions are weak. So like this, some temporary dipoles are produced, and the attractive forces developed between them are called London forces. And now if you study the characteristics of these solids, so here, if you study, so they comprise molecular, non-polar molecular solids. They have either atoms or non-polar molecules with non-polar covalent bonds. If you take a hydrogen, solid chlorine, solid iodine, argon, helium, so either atoms or non-polar molecules. And in these solids, the atoms or molecules are held by weak dispersion forces, and those forces are called London forces. Just now I explained. And these are soft. Why? Because forces are weak. These are not strong forces, right? The forces are weak, therefore these are weak. And there are no ions. There are no current carrying species. So obviously these are non-conductors of electricity, because there are neutral molecules who will carry the current. And they have low melting and boiling points because attractive forces are less. London forces, because of that they are soft. Because of weak forces, they melt. Their melting points and boiling points are low, and they are usually they are usually in liquid or gaseous state at room temperature. That's why maybe after giving that example, hydrogen is a gas, helium is a gas. Why here the discussion is going on solid? Actually, under specific conditions, if you reduce the temperature, if you increase the pressure, so what happened? Liquefaction, continuation to that, solidification, crystallization will take place. But here you can see these are usually in liquid are gaseous state, because at room temperature also these London forces are very weak. Those forces will be broken and the substance will be in which state? Gaseous state at room temperature. So they exist as solids at a super cool temperature. I told you, right? Very low temperature. So simple discussion, non-polar molecular solid. This is the molecule, this is the molecule, or now this is atom, this is atom. Most of the time, electron distribution is symmetrical. At a particular instant, it becomes unsymmetrical, right? And this is called, what do we call, a temporary dipole. It causes distortion of electron cloud in a second molecule also, and temporary dipoles are produced, and attractive forces are London dispersion forces. These are weakest forces. You can see there are no electrons, no ions, therefore they are non-conductors. Second one, polar molecular solids. Dipole moment is not equal to zero. Here always the students get confused between polar molecular solids and hydrogen bonded. Specific examples we have. Polar molecular solids, I will discuss this, but let me explain. For example, you can take a, see, this is a solid HCl, and this is a separate solid, right? Solid sulfur dioxide. HCl, it has a permanent dipole moment. Hydrogen with a partial positive charge, chlorine is with a partial negative charge. This is one dipole, this is one dipole, this is one dipole. Chlorine is negative pole and hydrogen is partial, what do we call, positive pole. Not ions, right? Between hydrogen and chlorine, there is a covalent bond. If it is added to water, then it will undergo ionization, right? I'm talking about the pure HCl solid, right? And here between chlorine and hydrogen, there are, what do we call, attractive forces. These attractive forces are called dipole forces. Dipole forces. Not only HCl, you can take sulfur dioxide also. Sulfur dioxide, you know, it is angular in shape, but you should not take carbon dioxide here. Carbon dioxide dipole moment is zero. Sulfur dioxide is angular molecule. sp2 hybridization and angular molecule, dipole moment is non-zero. Sulfur is positive pole, oxygen is negative pole. Between oxygen and sulfur, there are attractive forces. So in case of polar molecular solids, in one word, in polar molecular solids, what type of forces are present? Dipole-dipole interactions. These are not temporary dipoles. These are permanent dipoles. These are permanent dipoles. And what are the characteristics? Now let us study. So these are very clear, made up of polar molecules. We know polar molecules, how to check dipole moment. Molecules in these solids are held together relatively strong. Relatively, right? Relatively means when compared to the first one. When compared to the first one, here dipole-dipole interactions are relatively stronger. And these are also by nature, they are soft. Relatively, they may be strong, but by nature, overall, they are soft. Yes, there are no current carrying species. Already told you that is not ion. HCl, that is not ion. We are talking about solid HCl. Hydrogen and chlorine, they are held by covalent bond. But because of high electronegativity, electron pair is, instead of being at the center, that is more towards chlorine, right? So once again, that is not ion. So these are what we call non-conductors of electricity. Melting points and boiling points completely depend on intermolecular forces. When compared to non-polar molecular solids, in case of polar molecular solids, the force of attraction is relatively more. Hence, melting points are higher than those of non-polar molecular solids. But at most of these are gases. At most of these, HCl is gas, sulfur dioxide is gas. But sir, we are talking about a solid. But at super cool temperature, those solids are possible. Required temperature and required pressure. So this is the second type. But the thing is, this figure will help you. So if you take it as points, definitely it will be boring. But yes, what is dipole moment and how dipole moment is not equal to zero, how dipole is produced. And in case of solid HCl, the molecules are held by dipole-dipole interactions. When compared to dispersion forces, these are strong. When compared to that, this is relatively more melting and boiling points, right? Same picture, this one. Next one, we have one more category, right? Third one, hydrogen bonded molecular solids. Hydrogen bonded molecular solids, that means that substance should have the capacity to form hydrogen bond. But generally what I teach is, this is also dipole dipole attractions, but extreme form. This is extreme form. The magnitude of the charge what you are writing is relatively high. Extreme form of dipole dipole interactions, generally I teach like that. But constituent particles are molecules. So these are molecules which contain hydrogen atom linked to highly electronegative element such as fluorine, oxygen, nitrogen of neighboring molecule. So let us take the picture first. You can see this is ice. Otherwise, this is ammonia in ice. This is one water molecule. This green color thing is oxygen, and this is hydrogen, water molecule. And we can actually, this is also we can say dipole interaction. But when compared to dipole dipole interaction, here the magnitude of attractive force is relatively more. Hence, we are differentiating, right? So this is what do we call hydrogen, high electronegative element, oxygen, nitrogen, fluorine, and this bond is called hydrogen bond. Here the molecules are held by which bond? Hydrogen bond. You can see partial charges, and this is actually in this picture you'll be more comfortable, not that one. You can see this one. See, this is nitrogen. These are three hydrogens. Nitrogen, three hydrogens. Nitrogen, three hydrogens. So the bond is hydrogen bond. The molecules of ammonia in solid state are held by hydrogen bonds, intermolecular hydrogen bonds. Intermolecular, you can see between these two molecules there is one hydrogen bond. When compared to dipole dipole attractions, hydrogen bonds are strong. So here, that's why let us say, take the characteristics. These are also non-conductors, very clear. Conductor means it should have current carrying species. There are no ions, no electrons. Due to the presence of strong hydrogen bonds, these solids have higher boiling point, but strictly speaking, relative. But later I'll take ionic solids. When compared to ionic solids, this attractive force is weak. So this is relative comparison. So relatively, this hydrogen bond is strong, hence melting and boiling points are more when compared to non-polar solids and polar solids. Compared to non-polar solids and polar solids, so these melting and boiling points are generally high because hydrogen bond is strong. So what is the sequence? Crystalline solids, we started four types. First category, molecular solids. Constant particles are molecules. These are classified into three types. Three types we completed. Now let us take ionic solids. You're saying solid. What is the prefix you're adding? Ionic. Solids having ions. Solids having ions. Let me explain this with the help of pictures. Later we can understand. For example, if you take ionic solid, totally we have ionic solids. All examples are rock salt, cesium chloride, with all pictures, everything in detail we'll discuss. See, for example, let us take this. This is what do we call violet? Let us say this is a cation, anion, cation, anion, cation, anion, like this. Systematically the ions are present. That's why they are crystalline solids. They have long range order. They have long range order. So this violet thing is a cation, and a green thing, that is anion. What forces? Ionic bond, electrostatic forces of attractions. When compared to hydrogen bond, electrostatic forces of attractions are strong. Electrostatic forces of attractions are more. So like this, ions are present. See, by seeing this, due to the presence of ions, you may have a wrong notion like they are good conductors. No, no. In solid state, they are not conductors because ions are held very tightly. Ions cannot move towards opposite electrodes because cation, anion, they are held by strong electrostatic forces of attractions. Therefore, even though the constituent particles are ions, ions are not free. Hence in solid state they are insulators. You see, for example, this is this ionic solid. You see this ionic solid, and here I have taken what do we call polar solvent in the first glass. In the second glass I have taken benzene, non-polar. Water is polar. Polar solvent has the capacity to break the electrostatic forces of attractions. That capacity is called dielectric constant. The highest dielectric constant is possessed by water. Polarity of the solvent is measured by using dielectric constant. What is meant by dielectric constant? The capacity of the solvent to break electrostatic forces of attractions. Water has the capacity to break electrostatic forces of attractions between cation and anion. Hence, you can see this is called aqueous solution. In this aqueous solution, now the ions are free. There are no attractive forces between cation and anion. The ions are free. Now it is a good conductor. But what is our topic? Solids. That is not solid. Liquid, aqueous solution. So these solids in aqueous solution, they are good conductors. Very clear. But in solid state, they are insulators. But instead of water, if you take a non-polar solvent like benzene or carbon tetrachloride, if you add this, dielectric constant is less, very less, zero. That means that a solvent has no capacity to break electrostatic forces of attractions. Hence, you can see the lump is like that. The ions are not getting separated. So this is a bad conductor. This is a non-conductor. And see, actually, liquid can be obtained in two different, but this is not actually, this is not the liquid form of the substance. Still, you can see here that solid only. But this solid can be converted into liquid in two different ways. One is by dissolving in water. Another one is by dissolving in water. Another one is by heating above its melting point. Instead of water, you are giving heat. You are increasing the temperature of the solid. Whatever the heat you are supplying, that heat will break the electrostatic forces of attractions. Now you can see this is called molten liquid. This is aqueous solution. This is molten liquid. Here ions are what do we call dissolved in water, continuous medium. But this is a solution. This is only what do we call molten liquid of that particular solid. Yeah, there are free ions, but in solid state they are not. But in liquid state, either in what do we call, you may get it out, sir, this is also liquid. No, it is not liquid. Liquid state of that solid, no, definitely that solid lump is there. Liquid, that is carbon tetrachloride, you are talking about this ionic substance, right? So this is still, it is in solid state. So here, what do we call, this is molten liquid and this is aqueous solution. And what are the examples of ionic solids means n number of examples, because in this chapter totally we'll be learning ionic solids more after completion of internal structure. So whatever the things we learned, let us discuss fastly. These are, what are the constant particles? Ions. Very clear. Ions are the constant particles. These are formed by three-dimensional arrangements, systematic three-dimensional arrangements. What forces? Strong electrostatic forces, which are called ionic bond. Ionic solids are hard and but brittle in nature. They are hard, of course, but brittle. They are brittle in nature. And these solids have high melting and boiling points because ionic bond is strong. You just compare melting point of ice, melting point of NaCl, melting point of ice, 0 degree centigrade. Melting point of NaCl somewhere around 800 degrees centigrade. See the difference? See the difference? And these are electrical, very important points. Students always commit mistake here. So these are electrical insulators in solid state, because ions are there, but to show the conductivity, what is the condition? Ions must be free. Free ions are present either in molten liquid state or in aqueous solution state, but in solid state ions are held very tightly by strong electrostatic forces of attractions, therefore insulators. But in molten liquid state and in aqueous solution state, they are good conductors. You can see you can feel here current carrying species. You can see these ions will carry the current. So four types of crystalline solids, two types over, third one metallic solids. Third one, metallic solids. Yeah, you see here, in case of metallic solids also, first let us take the diagram. After that, we will talk about something. See, for example, if you are comfortable, you can assume in place of that yellow thing, sodium you assume. If you don't like sodium, you take magnesium, no problem. Some metal you assume. Because metallic solid means you have to take metal only. So here in the picture also, I've taken M plus. So you just assume Na plus. See, this is the structure of metal. This is the correct structure of the metal. In chemical bonding, you might have studied. This is actually electron C theory. See, this is the total volume occupied by the solid. This glass thing you can see in that container. In that, this is the volume, and at room temperature also, it is not called ionization. Actually, there are metal cations and free electrons. Actually, electrons are free because the mass of electron is very, very less. So we can say that this is the sea of electrons. Sea of electrons. In that sea, metal kernels are embedded. Metal kernel. So this is metal kernel that is in the form of ion. What is the evidence? Metals are good conductors in solid state. If it is not in the form of metal kernel and free electrons, how can you explain the conductivity? So there is one theory called electron C theory. According to that theory, if you take any metal at room temperature, in that metal there are metal kernels. These yellow things are metal kernels. Metal kernels are fixed at some place, but electrons are moving freely because of free electrons. Kernels are not moving. If you increase the temperature, okay, that will be done in electrochemistry in some other chapter. But here there are free electrons. Due to the presence of free electrons, they are good conductors. What is the bond? Metallic bond. Metallic bond, metal kernel and electrons. Metal kernel and electrons. Electrostatic forces of attractions. That bond is called which bond? Metallic bond. Of course, there is also one more theory, valence bond theory, but conductivity, that is explained by electron C theory. Constant particles are metal kernels. I have shown metal kernels and free electrons. Metal kernels are fixed at some positions, and electrons are mobile. Electrons are freely moving. Because of free electrons, it is a good conductor. They possess high electrical and thermal conductivity because of electrons. Melting points are fairly high. When compared to ionic solids, they may have less, but when compared to molecular solids, melting points are high for metallic solids. These are hard but malleable in ductile. You know that. So even though metal is hard, we can convert that metal into transparent sheets and wires. Copper wires we make. In chocolates we take aluminum foils, so they can be converted into transparent sheets and wires, malleable and ductile. Important characteristics of metals is their lustre, metallic shining. Metals are in color, they have colors. So metallic lustre and color in certain cases, so you can see copper, zinc, iron, aluminium, silver. So in brief, metal kernels and free electrons, due to the presence of free electrons, they are good conductors. When compared to molecular solids, definitely melting points are high. But when compared to ionic solids, melting points are less. Last one, that is covalent or network solids. Covalent or network solids. I told you these are made up of atoms of same or different elements. But the same thing, let us take a crystalline solid diamond. You know, diamond is an allotrope of carbon, and every carbon is attached to four other carbon atoms. A giant covalent polymeric solid. Diamond structure. Every carbon is attached to four other carbon atoms, right? And here, this is one example, and another one is graphite. Graphite. So this is hexagonal ring. Each ring is made up of carbon atoms. Every carbon is attached to 3 other carbon atoms. This is the first sheet. In graphite, this is the first sheet, and you can see, so this is sheet 1, sheet 2, sheet 3, sheet 4, sheet 5, like this. And between, there are van der Waals forces. Between the first sheet and second sheet, there are no covalent bonds. The covalent bonds are present only in one sheet. Each sheet is made up of hexagonal carbon rings. See, this is hexagonal. See, this is carbon, carbon, carbon. And every carbon has one free electron. And there are which forces? Van der Waals forces. Between layers, there are van der Waals forces. Except graphite, we have silicon carbide, that is called carborundum, right? Boron nitride we have. But except graphite, remaining covalent solids are insulators. You can see there are so many covalent bonds in case of so giant covalent polymeric solids. They may be atoms of same or different elements. If you take diamond, all are carbons. If you take silicon carbide, silicon and carbon. If you take silica, SiO2, silicon and oxygen. If you take graphite, only one element, boron nitride, boron and nitrogen. Inorganic graphite, that is also, but only graphite is conductor, remaining all covalent solids. The very important point, generally in mains kind of examination, those things will be tested. These are made up of atoms of same or different elements, and atoms in these solids are held by large number of covalent bonds. I have shown these are hard and brittle. These solids have extremely high melting points. If you compare melting points, first you will be getting covalent solids, this category, ionic solids, metallic solids, hydrogen bonded molecular solids, polar molecular solids, non-polar molecular solids. That is, melting point can be compared by taking intermolecular forces, interparticle forces into consideration. And here this is about, but graphite is soft. Generally they are hard, but graphite is soft. Why graphite is soft? Because between the layers there are only weak van der Waals forces. Between the first layer, second layer, due to the presence of weak van der Waals forces, the layers can slide over one another, and this is soft, and also it is conductor of electricity because there are free electrons. So this is the end of the second video. In this video we talked about different types of crystalline solids, and in the next video we'll be taking the internal part of crystalline solid, internal structure of crystalline solid, what is meant by unit cell, what is a space lattice, and with the help of diagrams, 100%. So here you will be getting the crystal clear clarity if you are watching all the videos thoroughly. Yeah, this is the end of second video. We'll be meeting in the next video. Thank you very much.